n is greater than or equal to 0, these ages are real numbers. It's the collection of all polynomials of various degrees place, including constant polynomials and polynomials of degree 0 or 0 polynomial. And or is this one? You add any two polynomials, you get another polynomial, right? These polynomials are going to enjoy all properties mentioned for V plus. In the place of V, I'm taking P. In the place of F, I'm taking R. Again, routine verifications, you can check that this is also going to become a vector space over R. Vector space over R. Now, let us just try to look at the case with this one. I want to look at some concrete example which has got some beautiful geometrical visualization. Consider this example. V is equal to R cube. This field is taken to be safe. Under the same usual operations, let for x bar is equal to x1, x2, x3, y bar is equal to y1, y2, y3 belonging to R cube. We shall define like this: x bar plus y bar to be coordinate wise addition, same, x1 plus x2, sorry, x1 plus y1, x2 plus y2, x3 plus y3. With this addition and a belonging to R, x bar belonging to this R cube, we shall define a x bar as a x1, a x2, a x3. If I look at this way of defining scalar multiple of x bar and addition of vectors like this, under again usual operations in R and R cube, this R cube over R is also a vector space, of course, over this. Let us see what actually this means geometrically. What actually this uses geometrically. Right? So what is it you are getting? These points can be identified. These points can be identified as this point and this point. These points can be identified as vectors in the three-dimensional space. Euclidean space of dimension 3, you can consider them as vectors in 3D space. If I add these two, what are the vectors? You can even identify these points with the position vector. If I call this point to be some P, this one to be Q, OP and OQs are going to denote denoted by x bar and y bar. So this x bar plus y bar is going to be nothing but a vector addition and nothing more than that. So usual vector addition is going to lead to this conclusion, right? And sometimes it so happens that some subsets of this R cube, they are also going to enjoy same set of properties as this bigger vector space enjoys. For instance, if I take W something like this, consider W to be the collection of all those x1, x2, x3 belonging to R cube, such that x1 plus 2x2 plus 3x3 is equal to 0. If I collect all such points of R cube into W, then this W is also vector space over this particular R. You can check this. This is going to enjoy all the properties that are enjoyed by original parent space, this R cube over R. And such spaces are called subspaces of original vector space V. Such spaces are called subspaces of subspaces, let us say. In other words, if I look at this particular thing geometrically, what actually the members of this W are? Can you look at this? Look at this particular thing. Let us try to look at the. If I look at this particular x1 plus 2x2 plus 3x equal to 0, I think, is it a plane passing through the origin? Please tell me. X1 plus 2x2 plus 3x3 equal to 0. It is nothing but a plane passing through the origin. Can we draw this? You can just see its visualization like this. I want to look at this visualization of this vector space. So let's look at this. X, instead of x1, x2, x3, I'm taking x, y, z. X plus 2y plus 3z is equal to 0. If you look at this one, and this is the space I'm talking about. This colored plane is the subspace of the original space. Original space is not what total space of points in the 3D space, and this is what I'm talking about. So this is nothing but the subspace that we have considered in the previous example. So for that matter, you take any concept in the linear algebra, you can visualize them very easily. But almost all the concepts have got some visualization, right? So having done this, let us go through our main topic. So it's nothing but here in this case, here this W is a plane as was seen, right? Now, concrete definition is this one. Suppose V over F is a vector space over A. Let W be a subset of V. Of course, W not equal to empty. If W itself is a vector space over this F, then under the same operations, of course, under the same operations as in, then this W is called a subspace of V. It's called a subspace of V. And don't worry, most of the times we can talk about these vector spaces and a lot of theory pertaining to these vector spaces in more general setting. But for our purposes, mostly we consider these vector spaces only, particularly R square over R cube over R, for that matter, R power n over R, and these are replaced by C. C square over C means the complex field. C cube over C or C power n over C. Even R over R can also be thought of as a vector space. C over C, these are all vector spaces. And these spaces are of prime concern to us. These spaces are going to play a dominant role in our theory. If you want to look into some beautiful illustrations or interactive examples pertaining to this vector space theory, I recommend you to look into this particular online textbook which is available on the internet for free usage. The textbook's name is this immersive linear algebra. Immersive linear algebra is an online textbook, online text with a lot of illustrative examples. A lot of illustrative and interactive examples. And interactive examples. And every concept related to this matrix algebra or these things, you can have some visualization, visual applications for that, mostly taken from the computer graphics. Shall I show you that particular textbook? Let me show you the
Yes.
textbook for a while so that you can feel the
Yes,
Yes.
yes, we do please for that.
presence of that. This is the one I'm talking about. Yeah, this is the textbook I'm talking about. Immersivemath.com. It is there in the website. Immersivemath.com. Even if you type immersive linear algebra, you will get this, okay? This is developed by three people, Strom, Astrom, and Moeller. These are the three people who have developed this particular content, which have got lots of illustrations. Starting from vectors, dot product, vector product, Gaussian elimination, matrix, determinants, rank, linear mappings, eigenvalues, and eigenvectors. So with these chapters, these things come to an end. Linear mappings are nothing but mappings between two vector spaces, which enjoy that linearity. If you look into this particular, yeah, let's just try to look at this dot product. So you can see the beautiful definitions in detail. There will be something like this, but you will have some lots of illustrations also, like this. You can just, I'm talking about this kind of interactive nature, you see. What actually is this? Of projection of u plus v onto this particular line that is shown here, okay? So such beautiful illustrative examples you can check here. You can see if this is the vector u and this is the vector v, and this vector is going to be u minus v, right? You can see this. If you go on changing these vectors, you can even look at this. So you can have the feel of total geometry which pertains to this algebra. So these algebraic concepts can be clearly viewed by using this particular tool, right? You can just see all this stuff. It's not interactive, please. You can see norm of a vector and so on. So these things come later when you look into this particular Hilbert space theory. And you please refer all the pages of this particular textbook so that you get very good understanding over the concepts done in the linear algebra, like even eigenvectors and eigenvalues. They have got lots of illustrations. For that matter, let me just look at one this thing. If you start with any matrix, say M, which contains the numbers 1, 2, 50, 65, 70, say 90, 2, 3, 4. Like if I take a matrix like this, if you look at this one as a matrix as it looks so dull. Of course, it has got some practical implications. But when you view this example from the computer science point of view, The if I look into a gray image, the image which is there in black and white, every image can be thought of as a gray image. A gray image can be thought of as collection of course, rectangular collection of pixels. Pixel in picture cells, small cells. When you look at an image, when you zoom it out, you will come to know that that's going to be a collection of some rectangular pieces, right? They are called pixels. More the number of pixels, the greater the clarity over the image, right? So every gray image of some figure, some portrait, can be thought of as a collection of pixels. So suppose that means this can be thought of as any image is a matrix of appropriate order, say m by n, with m and n's being large, of non-negative numbers. Non-negative numbers. But if each number is assigned with, suppose 0 is attached with 0 is to mean for black and 1 is meant for total white. And suppose if I take 256 numbers, 255 numbers, which range from 1 to 0, 1, 2, 3. So if you go on increasing the size of the number, the color pertaining to that one becomes whiter. So when you go on decreasing the numbers, that those pixels are going to become close to black. So a collection of these numbers between 0 to 255 can be, of course, matrix being, say, of order m by n, is going to be a matrix representation for the image, right? So it's going to be something like a matrix is nothing but can be thought of as a representation for a portrait of course, appropriate order m by n with so many entries, a11, a12, so a1n, a21, a22, etc., a2n, and so on, am1, am2, and so on, amn. You can think about this one as a matrix pertaining to some image. So what changes are going to take place while multiplying a row with some number, taking a submatrix of this matrix, or decreasing each number by some constant and increasing each number by some other constant in the matrix. All these things, where do they lead to? So these changes you can see in the image processing business, in the computer graphics, so nicely. I request you to look into an important book which addresses these aspects. Uh, the book's name is this one. Please refer this book. The book's name is this. When the life is linear. When the life is linear. This is the text, of course, published by American Mathematical Society. Published by American Math Society. You can see nice illustrations pertaining to all these matrix operations with numerous applications. To show you, let me go through that book and I would like to show you one or two images. That book is, I'm talking about this book. The book is this. So this is the book I'm talking about. So when the life is linear, when life is linear, it's produced by Ma. Let's try to look at one example from this. Almost all the properties or all the operation that we have done on the matrices, you can think about this. You know, 2.3. If I look at this, right? Yeah, look at this particular book. So this can be thought of as a matrix of order, say, some m by n. And if I take 303,888, it's going to be a submatrix. If you look at this particular figure, it's in fact, it's nothing but painting of Mona Lisa, right? Well-known image created with a printer and numbers, but so much less satisfying effect than with a brush and paint. It is not that type appealing as we paint this one with a brush, but certainly it looks like a Mona Lisa painting, right? Just look at this, what's going to happen. You can see some a cub and a male lion right here. If you look at the figures in C, what is done, you see? A part of this one, a part from the figure B is replaced with a part of this one. But this total picture, picture A can be thought of as a matrix. Picture B is another matrix, right? So each pixel is going to represent some color here. A part of this matrix, namely a submatrix, is removed, and in that place, some other submatrix is replaced here. As a result, this particular, which one, typical figures are appearing, isn't it? It's a typical combination of this cub line and this male line, bigger line, right? How this has happened? Nothing. You have just replaced a submatrix with another submatrix. The result is this. That's it. Yeah. If I look at the previous image, Mona Lisa's image, if I look at this image, it is a collection of some pixels, right? You can see it's a collection of pixels. It can be thought of as some m by n matrix. From each of the numbers in this particular matrix, if I decrease that number by some lesser number, we will be coming closer and closer to dark color, right? So picture becomes a bit dark in nature. When I add some number to all the entities, it's going to become brighter and brighter, right? Suppose if I just reverse the numbers, if I replace the number 1 by 0 and 0 by 1 and rest of them with the complements, it's going to be negative of the total image you get. Blacks becomes white, white becomes black, and others similarly. So negative is going to appear in simple operations. Simple matrix operations are going to lead to these kind of changes in it. Suppose if I multiply each of the entries in the matrix, a bigger image comes into picture, right? If I divide with some number each entry, again a smaller figure is going to come into picture. Same thing without any distortions. And all these stretching and shrinking, elongation, compacting, all these things can be done by manipulations on matrices. Theory of matrices is nothing but theory of vector spaces. So even eigenvectors can also be made use. Eigenvectors and eigenvalues, they can also be made use in detecting these images. Detection of images can be thoroughly be done by using eigenvectors and eigenvalues also. You can have some beautiful lectures in this particular book. You please go through this book also, which is published by American Math Society, When Life is Linear. So leaving this one aside for a while, when you look into R square over R, there you have got some, let us take X bar to be X1, X2, say Y bar to be Y1, Y2. We define X bar dot Y. These things can be thought of as vectors, position vectors of 2 points in the 2D plane, right? If I write X1, Y1 plus X2, Y2, this is nothing but a dot product of two vectors. And dot product of two vectors have got something to do with the angle between them, right? That connects size of the vectors and angle between them. That's what we have with us. So in this particular vector space, if I look into this kind of product, remember in the definition we have made a mention about addition of vectors, but we did not speak anything about multiplying vectors, right? In the vector space definition, only addition is imposed on this. You can just look at this. Only addition kind of operation is done in the vectors, but we do not know the method of putting some kind of products into this. For product of vectors, we did not speak, right? But my point is that when you talk about these vector spaces, not only addition, a kind of multiplication can also be done in this. And they are going to lead to entirely different aspects. I mean, let us try to look at that particular business. I'm not looking at all those aspects, namely linear independence, linear dependence, basis, dimensions, all this mathematical theory you are familiar with. I don't want to repeat them. Even if I touch them, the total time will be elapsed. Instead, let me just motivate you to go through some multiplication operation in the vectors. And they are going to produce a special kind of vector spaces. They are called inner product spaces. For that, let's try to look at how to introduce such a kind of operation in these vector spaces, taking motivation from this dot product of two vectors. And three vectors also you can have dot product. So taking motivation from that, I want to look at another concept, namely inner product spaces. Inner product spaces. These are nothing but vector spaces only. But the new thing is that we are going to define some kind of multiplication for the vectors. So further, let us start with a vector space. Let Ax be a vector space. Vector spaces are also called linear spaces. It has got another name linear space over either R or over C over K. Let me call over K over K, where this K is nothing but either R or C, where K is either R or C, right? K is either R or C. So let's take such a vector space X over R. And in this, I would like to denote the complex conjugate of for K belonging to K, denote the complex conjugate of K by K bar. If it is real, K bar is K only. Remember, K bar is equal to K if and only if K is real. For real, there is no problem. Same itself is going to come. For complex number, it's going to become its conjugate. Now I want to define an inner product on X as follows. So an inner product this on this X is a function from X square into K, satisfying these conditions. So it is nothing but a typical function which is defined on X square taking scalar values. So this is something like this. First point is this. satisfying number one condition is x plus y comma z is equal to x comma z plus y comma z. And second property is this, x comma y is a complex number because it's going to be there in k. So its conjugate is equal to y comma x. And another point is that x comma x should always be non-negative, not only to be non-negative. And there should be another property, of course, I must mention, third property. I should have mentioned this one as second one. I should mention this one as this kx comma y is equal to k times x comma, let me mention here, and there itself. And not only this is non-negative, this x comma x is 0 only when x is 0 vector. Whenever there is something, this is called an inner product on x. So any vector space equipped with an inner product, equipped with an inner product is called an inner product space. We can produce number of examples. Inner product space, right? So what is inner product space? With some extra kind of thing which is available for the vectors in x, namely x comma, what do they convey in the first set of properties? Tell me. If you look at this first set of properties, if you look at these two properties, what do they convey? They convey that this property says that linearity is there in first coordinate here. That is x plus y comma z is equal to x comma z plus y comma z, and kx comma z is equal to k times this x comma y, or kx comma y is equal to k times x comma y. These two properties say that the inner product is linear in the first coordinate or first factor. And you look at the second one, conjugate of the inner product x comma y is equal to the inner product y comma x. And inner product for x with itself is always non-negative, and this becomes 0 only when the vector is 0. Only when the vector is 0. What are all these xy's? These are nothing but vectors. Okay, they are drawn from this. They're all. What is k here? K is from the scalar. K may be the field of complex numbers or field of real numbers. This is called an inner product. And before going for examples, I want to look at one important point here, namely, we denote this x comma x, its non-negative square root, by this symbol, and we call this as norm of the vector x. Norm of the vector x. We call this one to be the norm of the vector x. It is nothing but it's a concept extended to the extended concept of length. When you take your r square over r, it is nothing but it's going to give us the length of this. So such a thing is called an inner product space. And a special kind of inner product space is called a Hilbert space. So before going for that Hilbert space business, I want to look at one or two examples. Let us try to look at r square over r. Consider this. Consider this example. R square over r. take this example and define x comma y or x bar comma y bar, where of course x bar is equal to x1 x2, y bar is equal to y1 y2. We shall define x bar comma y bar by x bar y bar is equal to x1 y1 plus x2 y2. Is it a mapping from, note that this particular is mapping from r square into r only. Can you recognize? Because this is a real number. You consider this is a real number. So each pair of vectors like this is being mapped onto a real number, a scalar. Each pair of vectors is mapped onto a scalar. We do not know whether this particular way of defining the things is going to satisfy these conditions or not. Linearity in the first variable, and this is called in fact positive definiteness. This property is called in fact linearity in the first variable. Linearity in the first coordinate or variable, whatever you call it. And this is called this particular thing is called this property, not this, in fact this is called positive definiteness. That we shall come later. Now we shall see, is it going to enjoy all those properties that we have mentioned in the inner product space? First one we shall see. So consider two vectors, x bar, y bar, and z bar, with of course x bar is equal to x1 x2, y bar y1 y2, and z bar say z1 z2. So how is that we are defining? We shall see first one. How much is this x bar plus y bar comma z bar? We shall try to look at this inner product. How much is this? I'm trying to verify the first property here. What is x bar, y bar? It is x1 x2 plus y1 y2 comma z1 z2. It's inner product. But this is nothing but you have to just add coordinate wise x1 plus y1 comma x2 plus y2 ordered pair comma z1 z2. How to go for inner product of these two? Inner product of these two we know. How to want to multiply this? It's nothing but x1 plus y1 times z1 plus x2 plus y2 times z2, right? Keep it there. It's how about this one? Tell me, x bar comma z bar plus y bar comma z bar. We shall find out. X bar is nothing but x1 x2 comma z1 z2 plus y1 y2 comma z1 z2. How to go for these inner products? Inner product first is nothing but x1 z1 plus x2 z2. For the second one, y1 z1 plus y2 z2 are the same. If I call this one as one, this one as two, are the same. You please check. x1 z1 is here, y1 z1 is here, x2 z2 is here, y2 z2 is here. Okay, say they are same. So even you can verify that. In fact, you can see this also. K x bar comma y bar inner product is equal to k times x bar comma y bar. You can check this also. So other properties also you can check, because if I take x comma x bar comma x bar, what is going to happen? Or you can even check that conjugate business. Okay, that the first, second property is this one. What is the conjugate of this? It's nothing but, what is this? Tell me. It's x1 y1 plus x2 y2's conjugate. Because we are dealing with real numbers here, it is same as x1 plus x2 y2. This is same as x bar y bar, or in fact it is same as y bar x bar. You can check that. Similarly, what is x bar comma x bar? It is x1 square plus x2 square, which is non-negative. And in fact, this x bar comma x bar is equal to 0 if and only if this x1 is 0 and x2 is also 0, which is going to give you that x bar is 0, right? So therefore, certainly this is an inner product on this r square. It's an inner product on r square. So therefore, r square over r is an inner product space. Why r square over r? With same logic, even r power n over r for n greater than or equal to 1 is an inner product space, right? But the case would be quite interesting when you deal with complex vector space over complex field. You consider this one as a second example. You consider Cn over C for x bar is equal to x1 comma x2, y bar is equal to y1 comma y2, C square let us take for that matter to illustrate this one easily, and where of course xj's and yj's are complex numbers. Define the inner this particular product x bar, this one to be x1 y1 conjugate plus x2 y2 conjugate. Now, is this a mapping from C square into C? See here, these are two vectors with coordinates being complex numbers, right? And x1 is a complex number, y1 bar is a complex number, product is a complex number, added to another complex number, it is a complex number. So therefore, this product is very much a mapping from C square into C. Done. But other properties also you can verify. Linearity in first variable you can check as we have done in the previous case, but here the definition is slightly different. X bar y bar is taken to be x1 y1 bar plus x2 y2 bar we have taken, rather than x1 y1 plus x2 y2 earlier, right? This is to make that second condition to work for here. Here also, if I take same definition as was the previous one, I think it's not going to become, not in that, it's not going to become inner product. Why? That second condition might fail. X bar, which is going to become in that case, x1 square plus x2 square comes in, that need not be a non-negative number, unless they are reals, okay? That is the reason to take something like this. In that, this is going to become an inner product on this C square. This x bar y bar is an inner product on this C square. Very good. So therefore, C square over C, with this particular kind of definition, it's going to be an inner product. Now I want to come back to this particular, look at this norm of x whole square. How much is this? I have defined square root of x comma x as norm of the vector x. So therefore, norm x square is how much? X comma x. So if I look at that, x comma x is nothing but, what is x here? x1 comma x2, or you can call x bar y, this one. So comma x1 x2, it's inner product. How much is that inner product? Tell me. It is equal to x1 bar plus x2 bar. So x1 is a complex number. Multiply that with its conjugate, which is nothing but modulus of x1 square. So it is nothing but modulus of x1 square plus modulus of x2 square, because x1 bar is modulus of x1 whole square. It's modulus of x2 absolute value. In fact, square of the absolute value of x1. This is the square of absolute value of x2. This is what we get. I think this is always non-negative, right? So if I look at this norm of x, what actually is going to give you? It is nothing but modulus of x1 square plus modulus of x2 square. Is it the length of the vector? Length of that particular? You can even, if you confine this one to the previous one, that was nothing but in fact length of that vector. You can check. So this typical inner product is going to throw some light for us to focus on this. In fact, we shall focus, taking motivation from this. I would like to look at one important aspect, namely, so let's take x to be an inner product space over K. Let x K be an inner product space. Inner product space. On this inner product space, I would like to define a typical concept, namely a distance for x comma y belonging to this capital X. Define d of x comma y to be norm of x minus y. Of course, for x and y's belong to capital X. And then this is going to satisfy, then this d satisfies three conditions. You can verify them. Routine verifications will do. First property is this: d of xy is non-negative, and this dxy is going to become 0 only when x is equal to y. You can check this. Second property, d of xy and d of yx, I see no difference. This is true, in fact, with any pair of elements drawn from the vector space X, wherein that inner product is there. What is this, in fact? It is the non-negative square root of x minus y comma x minus y inner product. Is it right? That is the way. So, and third property you can check for this is this. Please. Hello? It is less than or equal to d of x comma z plus d of z comma y.
Sorry to disturb you,
For
sir.
all, oh, it's okay.
There was some disturbance from the other side.
No,
Yeah.
it's okay. Even you can even stop me also for any doubts. From the chat box, if you get some doubts, please let me know.
Okay, sir.
Okay. Right. So if you find any questions in the chat box, please let me know. I would like to address them also. So this particular D is going to enjoy these properties. And I'm not going to verify these facts, and you can even try also on your own. Nothing great in this one, but if I want to prove this one, I have to forego so much of time. Not necessary also. You can refer any standard textbook to verify these. And when a particular D-like function like this satisfies these conditions, we say that D is a metric on X. And this D, in this case, is called a metric on X. Metric on X. This we call, in fact, we call this particular X together with D, a matrix space. And this is purely mathematical nature. Don't worry about the nomenclature. Don't worry about this. And when you look into metric spaces and what for that matter any space, you can talk about sequences, sequences and their convergence and so on and so forth. If every and the Cauchy sequences, convergent sequences, this business is there in your real analysis. People are familiar with sequences and their convergence, series and their convergence. When do you say that a sequence is a fundamental sequence or Cauchy sequence? And every real Cauchy sequence is convergent, and every convergent sequence is a Cauchy sequence that we know. So in the case of real sequences, Cauchy sequence are convergent sequences and convergent sequence are Cauchy sequence. These properties you know. But there are some metric spaces, there are some spaces like this, more general spaces like this, wherein a Cauchy sequence need not be a convergent one. But a metric space in which every Cauchy sequence is convergent, we call it a complete metric space. If every Cauchy sequence in X is convergent, then X is called a complete metric space. Complete metric space. Let us not worry about when a metric space is complete, when a metric space is not complete. Let us not worry about those examples. They form purely a part of your mathematics of MSc. Let us not worry about them. Instead, what I do is, when you consider this, consider R power n over R and C power n over C. These are complete inner product spaces. Such a complete inner product spaces are called Hilbert spaces. Complete inner product spaces. Complete inner product spaces. Complete inner product spaces are called Hilbert spaces. They are called Hilbert spaces. Remember, for our purpose in developing the theory pertaining to quantum computing, and mostly we will be concerned with only this kind of spaces. In fact, this kind of spaces we are concerned with, please, not the others. So, but any of these are complete inner product spaces. What is the inner product that is defined? If I take x bar comma y bar belonging to C power n, then inner product x bar comma y bar, of course, with x bar is equal to, what is x bar? It should be an n tuple with the complex coordinates, right? x1, x2, and so on, xn. Y bar, say y1, y2, etc., yn, where these xj, yj are complex numbers, please. If I define the inner product to be something like this, the inner product is sigma j is equal to 1 to n xj yj bar is an inner product on this particular C power n whole square, okay? C power 2n for that matter. Inner product on this one. So this inner product is going to give you, it's a norm. What is the norm of a particular dx bar y bar here? If you look at that particular thing, d of x bar y bar is nothing but a norm of x bar minus y bar, which is nothing but square root of x bar minus y bar, its inner product with itself, okay? This is what it is nothing but sigma j is equal to 1 to n. What is that inner product? xj bar. J is equal to 1 to n. xj bar. J is equal to 1 to n. That's what we get. But it's nothing but sigma j is equal to 1 to n modulus of xj square. Oh, xj minus, sorry, I made a mistake here. I had to write it carefully. It's not correct, please. What is the x bar minus y bar? It's nothing but square root of, what are the coordinates here? x1 minus 1 at sigma j is equal to 1 to n xj minus yj into xj minus yj's conjugate. This is what we have. It is nothing but sigma j is equal to 1 to n xj minus yj whole square. So this is the d. With this d, it's going to become a complete metric space, and it's going to be an inner product space. And these are the spaces which are of prime importance to us. These are all Hilbert's spaces. Hilbert spaces with the usual inner product, and of course with usual inner product, these are all Hilbert spaces. These Hilbert spaces are going to enjoy certain properties. I would like to make a mention here. Some properties you can just quote here. If x over k is an inner product space or Hilbert space, no problem. Inner product space, then we have several properties with this. Number one, from the definition itself, we can see this. Our definition says that inner product is linear in the first coordinate, but now that linearity is not guaranteed in the first coordinate, second coordinate, but with some change you can do that. Another property that x comma ky is that k bar times x comma y, which we call conjugate linear. This property is called conjugate linearity in second coordinate. And the others something like this. And if you are dealing with one of the vectors to be 0, it is going to become 0 scalar. Remember, this inner product is a scalar basically, right? Inner product is a scalar. Even you can have several other nice examples of these inner product spaces. And for the moment, I want to look at another typical example, which also going to find some applications here and there. Let us consider these sequences. Let us take L square to consider the sequences like this. Namely, these are the sequences xj's, where xj's are complex numbers, and moreover sigma modulus of xj whole square, they are finite. So what do they mean? They mean that it's nothing but a collection of all complex sequences which are absolutely convergent, which are of course absolutely convergent. You can see this, or which are with this property, please. J is equal to 1 to infinity. This is called a square summable series. Some people call this one as square summable series. So this is L square. Then you can see that L square can be made into this L square over C is a, in fact, is an inner product space, you can check with the inner product. So inner product xj comma yj, inner product of these two sequences being equal to sigma j is equal to 1 to infinity xj yj bar. So this is the inner product which we are defining. With this inner product, it is going to become, in fact, a inner product space. Not only that, this is going to lead to the complete inner product space, which is going to become a Hilbert. In fact, this L square over C is a Hilbert space. When you talk about these Hilbert spaces, again, there come so many other problems. Because basically Hilbert spaces are linear spaces. You can look for mappings between these Hilbert spaces. If H1 comma H2 are two Hilbert spaces, then a mapping T from H1 to H2 is called a linear map or linear transformation. If that linearity conditions are fulfilled, T of u plus v is equal to Tu plus Tv, and T times alpha u is equal to alpha times Tu. Of course, for all u comma v is belonging to H1, alpha belonging to scalar belonging to this scalar. Alpha is a alpha scalar. Remember, here both H1 comma H2 are spaces over same scalars. That's what we have taken place. They're over K only. So you can talk about these linear spaces. When you talk about linear spaces, when the linear space is only from Hilbert space H into itself, we call it a linear operator. And these linear operators are going to lead to, when the mapping is only from H to H, we call them to be linear operators. And a knowledge of these linear operators is also required in order to understand that your quantum computing. But remember, whenever you talk about these linear operators, you can look for a basis of H, a basis of this one, and through that basis, you can describe images of all the elements of this particular H. You can even talk about these linear operators are going to be described. These are represented by appropriate matrices. With standard basis. These are some technical terms. I don't want to go into the details. Because these two are Hilbert spaces, you can have a basis for a standard basis for H. In the case of C power n, standard bases are nothing but 1, 0, 0, 0, 0, 1, 0, 0, etc. That's called standard basis. With respect to that standard basis, you can have a, given any linear operator, you can have an appropriate matrix which can be attached with this H. That means operators can be identified with matrices, and the matrices are going to give you some operators. So this total operators on Hilbert spaces, you can even look into the theory of matrices. So remember, roughly speaking, what is going to happen is starting with matrix algebra, matrix additions, square matrices, with eigenvalues, eigenvectors, and product of matrices and so on, determinants, etc. Starting with matrix theory, you can go through the generalization of this matrix theory to the vector space theory. From vector space theory, we go into the inner product spaces. From inner product spaces, we go into Hilbert spaces. When Hilbert spaces are confined to only these Cn over C or Rn over R, then you can look for mappings between R power n into R power n, which we call operators. These operators have got some matrices which represent that operator. And for that matter, every matrix is going to give rise to some appropriate transformation between two these Hilbert spaces. And in other words, even though we have talked about great about Hilbert spaces and then linear operators satisfying these conditions, which have come through so many other things, ultimately linear operators are going to boil down to what? Matrices. And matrices are going to give you some linear operators. So therefore, in order to study the linear operators, it is better to focus on the matrices corresponding to them. And when you take out these matrices, uh, for that matter, linear operators, these linear operators fall into various categories: positive operators, negative operators, positive definite operators, unitary operators. There are several kinds of operators are there. From among them, unitary operators are of greater importance, and Hermitians, Q-Hermitian matrices, and so on and so forth. These are various kinds of matrices, accordingly, various kinds of operators. A knowledge of these kinds of operators is required in order to understand the concepts of quantum computing and quantum information, and how these things are going to help us in understanding quantum computing will be clear through the lectures that are going to listen from today onwards. You might already stepped into quantum computing with the introduction of qubits and the states, Bragg notation, Keck notation, and all those things you might have seen in terms of linear spaces or vector spaces. And then you might have gone through the other aspects of these brackets and, or states and so on and so forth. We shall try to once again meet with Shore's algorithm, which is going to challenge the RSA crypto system. Till now, RSA crypto system is dependent on factoring an integer, and factorization of an integer is a tough problem. When you are dealing with integers containing, say, a few hundreds of digits, that problem is considered to be very tough. But that toughness is challenged by Peter Shore, uh, who says that that problem can be done easily by using quantum computing techniques, wherein he gives us an algorithm by name Shore's algorithm. Still, we do not know whether that is going to give a big challenge to the RSA crypto system or not. That we'll come to know about it in the last lecture. I would like to meet again you with the Shore's algorithm. And for the moment, I want to stop here, and you're open to pose questions, please, if any.
I have already put in the message, sir.
Uh,
Are there any questions? Participants?
Read out one question, please. From your end. Open and
No,
read out.
there are no questions yet, sir,
Okay.
in
Oh,
the
okay.
chat box.
Okay.
Okay. Yes.
Shall I conclude?
Yes, sir. I'll. Raj Reddy, sir, I would like to go ahead with the vote of thanks, or you want to speak?
Thank you very much, sir. You given a very elaborate lecture, sir. Starting from matrices to Hilbert spaces, sir. We are, we are thankful to you, sir, on behalf of the department and myself, sir.
Yeah, thanks to you also.
Sir, I would like to conclude with the
Okay.
talks remarks. Thank you, sir. It was really enhancing our knowledge. You started your lecture with vector spaces introduction. Then you even spoke about the subspaces and how we are going to go in detail of Cn of C and Rn of R. Then you even introduced us to two new books, which one is obviously an online book. I don't know about the second one book also, sir. The image processing, you have spoke about the image processing using the reduction of the order of the matrix. The reference book that you have suggested was When the Life is Linear. It was really a
Yes.
experience browsing those books, sir. You have
Yeah.
opened new horizon for us. We were limited to very few books, and then very limited confined study was there. Now you have taught us to think beyond the lines. Yeah, then you have introduced us to the concept of inner product spaces. Then special type of inner space is called the Hilbert space. Later we were introduced to metric spaces, complete metric spaces, and complete inner product spaces are called Hilbert spaces. When we are extending our work to Cn of C and R par n of R, we were taught about linear operators, and to understand the linear operators, matrix play an important role, where we will be corresponding matrix study will help us to go in detail of this quantum computing. Really, sir, it was like connecting all the dots. We were having all the knowledge, but they were not connected. With your lecture, we have enriched that knowledge and hope you to learn more in the coming session. Thank you, sir.
Yeah. Thank you, madam. Thank you so much.
Uh, can I close the session, sir?
Yes,
Uh,
please.
yeah. Uh, all the
Thank you,
participants.
sir.
Yes. Is anyone here to speak? You can. Okay. On behalf of the CBIT family, I thank all the people, the participants, and the presenters, speakers, all the dignitaries over here. We are done for the day. We'll meet you again tomorrow as per the schedule. Thank you,
Madam,
Madan.
one
Yes,
minute.
sir.
Madam,
Yes, sir.
being a coordinator, I want to tell you today all the three sessions are basically that background of the quantum computing. So basically, this quantum computing is dominated by vector spaces, and tomorrow you can go through that what is the actual quantum computing, how we can use what is the qubits and superposition entanglement and Bell state. Then come to the quantum information by Triviality professor. Uh, he is coming and he is going to be deliver the lecture in second session, and third session also IIT Gauti, some Goswami. So tomorrow the two sessions and including my session is the first session. I want to give the non-neglect of this all quantum computing, how we can apply these vector spaces to quantum computing, how this vector spaces, Hilbert spaces, how we can apply to the quantum computing. If you learn that is a basics, that is special, special notations are there. If you learn the special notations, then your path is very easy to go to the last phase of that quantum computing. You have to learn algorithms and execute algorithms. So that these are the basics. So I request all the participants, try to attend all the sessions so that you will get the knowledge and you can understand easily, because it is somewhat difficult. See, some faculty members are came from the background of the chemistry, some from physics, maths, and engineering. They can understand little bit. Even engineering faculty also little bit understanding difficulty in all these vector spaces and all. So this is a backbone of this. Particularly the vector space and Hilbert space are backbone of the quantum computing. If anything defined in the space, you require the vector space and Hilbert spaces applications. So you can see the beauty of the quantum computing tomorrow onwards. I hope that will give the path to learn more and more. Thank you very much for all participants patiently listening this all the three lectures with a gap of only 15-20 minutes. And I am seeing my colleagues, uh, uh, some of them are on the. Thank you very much for all of you. Madam, give that
Yes, sir.
conclusion.
Ma'am,
Yes.
dear coordinators, I have a request because we are, I mean, not everyone, I don't think everyone has a full network all the time. So the network keeps on breaking. If you can share the recorded session link, that would be
Okay,
really
definitely,
great.
Yes.
definitely, madam. The only
Sure,
thing is
sure.
you have to admit that 80% of the attendance. That is
No,
a,
no, sir, attendance will be there. The problem is, sir, like when I'm speaking, I can hear it after a minute. What
Okay,
others
okay.
are saying.
I got your problem, ma'am.
I will send if anybody ask one of the co-coordinators, they will send you a link. On that
Okay.
links all the sections.
Okay.
So don't worry about all. But only thing is, if you're regular, then you can understand more and more. Our aim is
Yeah, yeah.
to execute algorithms at end of that will come at the end of the 2 days. So all
Okay.
this you have to link to the quantum Fourier transform. Then you have to write the algorithm based on that. That is what a Duet's algorithm, Duet-Jose algorithm, Shor's algorithm, Siemens algorithm. So that actually, if you don't know this before these fundamentals, it is very difficult to understand. Even notations are very not complicated. It is teaching you to learn that is because always all notations are usual notations. This notation came from the Russian notation. The Russian people found this notation, and this is so that all notations are like this. So that is called a, we can call that is a different. You can get a column or like bra or vector like that. You can give the names. Tomorrow I will give the nomenclature of all these parameters, Then I will give this extension of the qubits and all. It will come in the next sessions. Okay.
Yeah. Ma'am, we will take care of this problem that you are facing. We will bring and we will try our best to share the recorded videos also with with respect to time. Thank you. I hope if you have any queries, you can put it in the chat box, or you can put us a mail also. No issues. We are here to make the things very comfortable so that the presenter and the learner both can take it in a better way. Thank you, one and all. See you tomorrow as per the schedule.
Thank you, ma'am.
Thank you.
Thank you, sir.
Thank you, sir. Yes.
Venugopal sir.